While physical eschatology makes a brief appearance in the movie, The Theory of Everything, it is cosmogony that dominates. The film focuses on two cosmogonic theories which Stephen Hawking has defended. The first being the standard Big Bang model based entirely on the general theory of relativity. And the second being the so-called no-boundary proposal, which Hawking developed in collaboration with James Hartle of the University of California, Santa Barbara, based on the incorporation of quantum physics into the standard model to yield a quantum theory of gravity. The film explores the alleged theological implications of these two theories. So that we might better understand these alleged theological implications, let me say a bit about these two approaches to cosmogony. First, the standard general relativistic model. Prior to the 1920s, scientists had always assumed that the universe as a whole was stationary and eternal. Tremors of the impending earthquake that would topple this traditional cosmology were first felt in 1917, when Albert Einstein made a cosmological application of his newly discovered gravitational theory, the general theory of relativity. To his chagrin, Einstein found that general relativity would not permit an eternal static model of the universe unless he fudged his equations to offset the gravitational effects of matter. During the 1920s, the Russian mathematician Alexander Friedmann and the Belgian astronomer Georges Lemaître, by taking Einstein's equations at face value, came up independently with models of an expanding universe. In 1929, the American astronomer Edwin Hubble, through tireless observations at Mount Wilson Observatory, made a startling discovery which confirmed Friedmann and Lemaître's theory. He found that the light from distant galaxies appeared to be redder than expected. This red shift in the light was most plausibly due to the stretching of the light waves as the galaxies are moving away from us. Wherever Hubble trained his telescope in the night sky, he observed this same red shift in the light from the distant galaxies. It appeared that we are at the center of a cosmic explosion, and all of the other galaxies are flying away from us at fantastic speeds. Now, according to the Friedmann-Lemaître model, we're not really at the center of the universe. Rather, an observer in any galaxy will look out and see the other galaxies moving away from him. This is because, according to the theory, it is really space itself which is expanding. The galaxies are actually at rest in space, but they recede from one another as space itself expands. The Friedmann-Lemaître model eventually came to be known as the Big Bang theory. But that name can be misleading. Thinking of the Big Bang as a sort of explosion could mislead us into thinking that the galaxies are moving into a pre-existing empty space from a central point. That would be a complete misunderstanding of the model. The theory is much more radical than that. As you trace the expansion of space back in time, everything gets closer and closer together. Eventually, the distance between any 2 points in space becomes zero. You can't get any closer than that. Space and time cannot be extended further back than that. So at that point, you've reached the boundary of space and time. It is literally the beginning of space and time. To get a picture of this, we can portray our three-dimensional space as a two-dimensional disk, which shrinks as you go back in time. Eventually, the distance between any two spatial points becomes zero. So, space-time can be represented geometrically as a cone. What's significant about this is that while a cone can be extended indefinitely in one direction, it has a boundary point in the other direction. Because this direction represents time and the boundary point lies in the past, the model implies that past time is finite and had a beginning. Because space-time is the arena in which all matter and energy exist, the beginning of space-time is also the beginning of all matter and energy. It's the beginning of the universe. Notice that there's simply nothing prior to the initial boundary of space-time. Let's not, however, be misled by words. When cosmologists say there is nothing prior to the initial boundary, they do not mean that there is something prior to it, and that is a state of nothingness. That would be to treat nothing as though it were something. Rather, they mean that at that boundary point, it is false that there is something prior to this point. The standard Big Bang model thus predicts an absolute beginning of the universe. In the movie, the standard model is described in the following exchange between Hawking and Jane. Hawking says, if Einstein is right, if general relativity is correct, then the universe is expanding, yes? Yes. So, if you reverse time, the universe would get smaller. All right. So, what if I reverse the process all the way back to see what happened at the beginning of time itself? The beginning of time itself? The universe getting smaller and smaller, denser and denser, hotter and hotter, as we wind back the clock. Keep winding. You've got to go all the way back to the beginning of time. Keep winding until you get a space-time singularity. The standard model thus predicted an initial singularity. There were, however, suspicions that since the real universe is not perfectly similar to Friedman and Lemaitre's ideal model, their prediction of a singular beginning to the universe would ultimately fail. Perhaps the distribution of matter and energy in the real universe is not homogeneous enough for the universe to shrink down to a singularity. In 1970, however, Hawking, in collaboration with Roger Penrose of Oxford University, proved that the assumption of ideal homogeneity was irrelevant. The Hawking-Penrose singularity theorems showed that so long as the universe is governed by general relativity, our past must include an initial singularity. Now, such a conclusion is profoundly disturbing for anybody who reflects on it. For the question cannot be suppressed. Why did the universe come into being? Sir Arthur Eddington, contemplating the beginning of the universe, opined that the expansion of the universe was so preposterous and incredible that I feel almost an indignation that anyone should believe in it, except myself. He finally felt forced to conclude the beginning seems to present insuperable difficulties unless we agree to look on it as frankly supernatural. In a scene deleted from the final cut of the movie, Jane and Hawking reflect on the implications of the Hawking-Penrose singularity theorem. Jane says, "This is amazing. This is poetry." Well, it's black hole theory. Time began at a certain point. There was a moment of creation. Yes, this is God's work. I think you'll find the equations are mine, but good point. The standard Big Bang model thus predicts an absolute beginning of the universe. If this model is correct, then we have amazing scientific confirmation of the theological doctrine of creation out of nothing. So, is the standard model correct? Or more importantly, is it correct in predicting a beginning of the universe? Despite its empirical confirmation, the standard Big Bang model will need to be modified in various ways. The model is based, as I've said, on Einstein's general theory of relativity. But Einstein's theory breaks down when the universe becomes shrunk down to subatomic proportions. We'll need to introduce quantum physics at that point, and no one is sure how this is to be done. The second cosmogonic model mentioned in the film is just such an attempt to marry quantum physics to general relativity to craft a quantum theory of gravity that will enable us to describe the early universe. The so-called no-boundary proposal, developed by Stephen Hawking in collaboration with James Hartle, who oddly enough is never mentioned in the film, is known as the Hartle-Hawking model. The Hartle-Hawking model eliminates the initial singularity by transforming the conical geometry of classical spacetime into a smooth, curved geometry having no edge, so that spacetime resembles a badminton shuttlecock. This is accomplished by the introduction of imaginary numbers, like the square root of -1, for the time variable in Einstein's gravitational equations, which effectively eliminates the singularity. The laws of physics thus do not break down at any point, allowing a complete description of spacetime. In his best-selling popularization of his theory, A Brief History of Time, Hawking reveals an explicitly theological concern. He concedes that on the standard model, one could legitimately identify the Big Bang singularity as the instant at which God created the universe. Indeed, he thinks that a number of attempts to avoid the Big Bang were probably motivated by a feeling that the beginning of time, and I quote, smacks of divine intervention. He sees his new model as preferable to the standard model because there would be no edge of space-time at which one would, and I quote, have to appeal to God or some new law. Hawking sees profound theological implications in the new model. He writes, "The idea that space and time may form a closed surface without boundary has profound implications for the role of God in the affairs of the universe. So long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. What place then for a creator?" Hawking does not deny the existence of God, but he does think that his model eliminates the need for a creator of the universe. In the movie, the theological implications of the Hartle-Hawking model are raised in a conversation between Jane, Stephen, and their friend Jonathan. Jane begins, "Stephen's done a U-turn. The big new idea is that the universe has no boundaries at all. No boundaries, no beginning. Oh, and no God. Oh, I see. I thought that you proved that the universe had a beginning and thus a need for a creator. My mistake. No, mine." Stephen is looking for a single theory that explains all the forces in the universe. Therefore, God must die. Oh, why must God die? I don't see. The two great pillars of physics are quantum theory, the laws that govern the very small, particles, electrons, and so on, and general relativity. Yes, Einstein. Einstein's theory, the laws that govern the very large, planets and such. But quantum and relativity, don't tell me, they're different. They don't play remotely by the same rules. If the world were all potatoes, then easy, you could trace a precise beginning, as Stephen once did. A moment of creation. Hallelujah, God lives. But if you incorporate peas into the menu, then it all goes a little haywire. This all becomes a godless mess. Oh dear. God is back on the endangered species list. Well, I expect he'll cope. As Jonathan rightly discerned, the theological implications which Hawking seeks to draw from the model are highly suspect. There is no reason at all that God could not have created a universe described by the Hartle-Hawking model. When I spoke personally with James Hartle in his office at UCSB, he saw absolutely no theological implications in the model. Indeed, by positing a finite imaginary time on a closed surface prior to the Planck time, rather than an infinite time on an open surface, such a model actually seems to support, rather than undercut, the fact that time in the universe had a beginning. Such a theory, if successful, would enable us to model the beginning of the universe without an initial singularity involving infinite density, temperature, pressure, and so on. But as physicist John Barrow of Cambridge University points out, this type of quantum universe has not always existed. It comes into being, just as the classical cosmologies could. But it does not start at a Big Bang where physical quantities are infinite. Barrow points out that such models are often described as giving a picture of creation out of nothing. The only caveat being that in this case, there is no definite point of creation. Hawking's crucial misstep is his assumption that having a beginning entails having a beginning point. Ancient Greek paradoxes about starting and stopping have long since taught us otherwise. Imagine that a cannonball has a last instant at which it is at rest before being fired from the cannon. In such a case, there is no point at which the cannonball first begins to move. For at any point after its final instant of rest, there will be a prior instant at which it was already in motion, ad infinitum. Yet no one would say that the cannonball does not have a finite trajectory and a cause of its motion. So having a beginning does not imply having a beginning point. Time begins to exist just in case for any finite temporal interval you choose, there are only a finite number of equal temporal intervals earlier than it. That condition is fulfilled for the Hartle-Hawking model as well as for the Standard Model. Moreover, it's far from clear that on any realistic interpretation of the Hartle-Hawking model, it does not in fact have a beginning point. By using the mathematical artifice of imaginary time, Hawking is able to re-describe the universe in such a way that it has no initial singularity. Hawking admits, only if we could picture the universe in terms of imaginary time would there be no singularities. When one goes back to the real time in which we live, however, there will still appear to be singularities. Hawking's model is thus a way of redescribing a universe with a singular beginning point in such a way that the singularity is transformed away. But it is the same universe with a beginning that is being described. Thus, quantum gravity models, like the Standard Model, imply the beginning of the universe. In his later book, The Grand Design, co-authored with Leonard Mladenov, Hawking himself seems to endorse this interpretation of the model. The authors write, "Suppose the beginning of the universe was like the South Pole of the Earth, with degrees of latitude playing the role of time. As one moves north, the circles of constant latitude representing the size of the universe would expand. The universe would start as a point at the South Pole, but the South Pole is much like any other point. To ask what happened before the beginning of the universe would become a meaningless question because there is nothing south of the South Pole. In this picture, space-time has no boundary. The same laws of nature hold at the South Pole as at other places." This passage is fascinating because it represents a rather different interpretation of the model than what we had in A Brief History of Time. Let me explain. In his model, Hawking employs imaginary numbers, like the square root of -1, for the time variable in his equations in order to get rid of the initial cosmological singularity, which is the boundary of space-time in the Standard Model. The initial segment of space-time, instead of terminating in a point like a cone, is rounded off like a badminton shuttlecock. The South Pole of this rounded off surface is like any other point on that surface, and hence the idea that there is no boundary or edge. Since imaginary time behaves like a dimension of space, Hawking interpreted his no-boundary universe to just be. But in the Grand Design, the South Pole is interpreted to represent the beginning point to both time and the universe. Hawking allows the circles of latitude to play the role of time, which has a beginning point at the South Pole. When Hawking speaks of the problem of time having a beginning, what he means is the age-old objection to the universe having a beginning, an objection which his model removes. So, what is that age-old objection? The objection, he says, is the question, what happened before the beginning of the universe? Hawking is right that this question is meaningless on his model. But what he fails to mention is that the question is also meaningless on the Standard Big Bang model, since there is nothing prior to the initial cosmological singularity. On either model, the universe has an absolute temporal beginning, so that it is meaningless to ask what happened before. Rather, the real question is, why did the universe begin to exist? The Hartle-Hawking model doesn't address that question. How could it? Physics only begins at the South Pole in the no-boundary model. There is no physics of non-being. Moreover, there isn't anything in the model that implies that that point came to be without a cause. Indeed, the idea that being could arise without a cause from non-being seems to be metaphysically absurd. Thus, both the Standard Model and the Hartle-Hawking quantum gravity model are united in predicting the finitude of the past and the beginning of the universe. And Hawking's inferences about the theological implications of the model are based on philosophical mistakes. It's sad that so gifted a scientist could have been misled by such philosophical missteps. Both models are thus perfectly in accord with the Judeo-Christian doctrine of creation out of nothing.